Okay, so in this video, we will consider more examples of evaluating indefinite integrals or finding antiderivatives. So let's recall our three results that we have so far. We have the power rule. So if you integrate x to the n dx, where n is a fixed constant, the power rule says you add 1 to the exponent, you divide by the new exponent, and you add, of course, the arbitrary constant of integration. Of course, this breaks down if n is equal to -1, as we'd have a division by 0. So we have the general power rule except when n is -1. And when n is -1, x to the -1 is 1 over x. And in this case, if you integrate 1 over x, thinking again of antiderivatives, we are looking for a function's derivative is 1 over x, that is ln, and remember, not just of x, but of the absolute value of x, again, plus c. So this is our general power rule with the exceptional case of 1 over x. And we have two very basic properties. If you integrate a constant times f of x dx, you can pull the constant outside of the integral. And if you integrate over a sum of, or a difference of functions, so suppose you integrate f of x plus or minus g of x, you can integrate the functions individually. So you can first integrate f of x with respect to x, plus, if it's a plus, minus, if it's a minus, the integral of the second function g of x dx. And these properties should be very easy to remember, as the derivative has the same properties. The power rule, of course, is a little different. So let's see how we can combine. We'll start easy with this property, this one, and then we'll combine the two with the power rule. And then you'll see that we'll do things in a long way first. And once you get the idea, we'll be able to find the antiderivative to our function much more efficiently. Suppose we start with the integral of 2x cubed. Well, it's not exactly the power rule, as we have to have a single power of x. Here there's a constant multiple, so we can factor it out. So this would be quite simply 2 times the integral of x cubed dx. So it's 2 times. And now we can apply our power rule after applying this first property, pulling the constant multiples outside. The power rule in x cubed says x to the 4 over 4 plus an arbitrary constant. And here's where it's interesting. Now we can multiply by 2. Well, 2 over 4 is 1/2, so it's x to the 4 over 2 plus 2c. And here I'll abuse the notation a little bit. If you remember, c is an arbitrary constant. So if c is an arbitrary constant, so is 2 times c. So to simplify, I'll simply rewrite 2c as just c. And the understanding here is that these are not the same c. The understanding is that this plus c stands for an arbitrary constant. As c is an arbitrary constant, so is 2c. So this is okay. Let's look now at this property. Suppose we wanted to integrate x cubed minus x to the 7. Well, this property says we can split the integrals into two separate integrals. So we can integrate x cubed dx minus integrating x to the 7 dx. And now both can be obtained from the simple power rule. X to the 4 over 4, and I'll write plus c1, as both will give us an arbitrary constant, and then minus power rule again on x to the 7, x to the 8 over 8 plus some other arbitrary constant. And we'll play the same game that we played in the previous problem. So if we look at what we have here, we have x to the 4 over 4 minus x to the 8 over 8 plus, and look at the arbitrary constant, c1 minus c2. But if you think about it, C1 is an arbitrary constant, C2 is an arbitrary constant. Therefore, a difference of arbitrary constants is also an arbitrary constant. So we'll just replace both of these by plus C. So we have x to the 4 over 4 minus x to the 8 over 8 plus some arbitrary constant. So you see when you have a sum or difference of several indefinite integrals, you don't need to add an arbitrary constant for each one. You just have to wait until the end. So x to the 4 over 4, x to the 8 over 8, and then you add the arbitrary constant. Because think of if we had a sum or difference of 20 of those, we wouldn't want to write C1 plus C2, C3 up to C20. We'll just add the n plus C. Now let's do one problem where we simultaneously will have to apply this property and this one and the power rule. We'll do it first a long way, and then I'll show you how, once you understand how to apply these rules, we can do it much more efficiently. So suppose we start with the integral of, and we'll go with just 3 terms here. Let's go with 2x cubed plus 1/2 x to the 9 minus, let's go with the 4th root of x dx. So we'll apply here, we're integrating a sum difference of 3 functions. So we'll apply here, of course, the third property, that we can integrate over a sum or difference each function individually. So we'll integrate 2x cubed first, plus we'll integrate the second function, 1/2 x to the 9, minus the integral of the third function, 4th root of x. Now we've separated the functions, and now we can apply, of course, the first property. We can pull constant multiples outside of the integral. Well, here we have 2 such constant multiples, so let's pull them out. So we'll have here 2 integral of x cubed dx. Pull the 1/2 out, plus 1/2 integral of x to the 9 dx. There is no constant multiple here, but we know we want to apply the power rule. So we'll rewrite, of course, a 4th root as a power of 1/4. And now we are left with 3 simple integrals, and each one is a simple power of x. And we can, of course, apply the general power rule, as none is 1 over x, which is our exceptional case. So, what do we have? 2 power rule x to the 4 over 4 plus 1/2. Power rule, we add 1 to the exponent, so x to the 10 over 10 minus x to the power rule again. We add 1 to the exponent. 1/4 plus 1 is 5/4. And here again you can be slick. If you divide by 5/4, you multiply by the reciprocal, which is 4 over 5. And now that we have integrated all 3 functions, then at the end don't forget to add the arbitrary constant of integration. We could simplify a little bit. 2 over 4 is 1/2, so we get x to the 4 over 2 plus x to the 10. 2 times 10 is 20 minus 4 over 5, 4/4. X to the 5/4 plus c. Okay, but this is way too long, right? I only did it to show you, to really break down what operations, what properties we used. First property, then we factored out the multiples, and then we use the power rule in each one. Let me show you how we can go from here to here, and this will give us a much shorter solution, a lot less writing. What we'll do is we'll apply these properties in our head, just as you would do if you were to take the derivative of this function. Once you get comfortable with the properties, you do it in your head. So we start with the integral of 2x cubed plus 1 over 2 x to the 9 minus the 4th root of x dx. Okay, so we integrate 2x cubed. The 2 is a constant multiple, it stays there. Power rule on the x cubed, x to the 4 over 4. Check. plus we integrate the second function. 1/2 is a constant multiple, it stays there. X to the 9th power rule, x to the 10 over 10. Done. Minus, and here again we think of the fourth root of x as x to the 1/4. So we use the power rule. 1/4 plus 1 is 5/4. Divide by 5/4, you multiply by 4 over 5. And of course now we add plus c. And this is how from now on you can do it. You can skip these two steps in terms of writing them out explicitly and just do it in your head, and this will save you a lot of writing. And of course now here again you would simplify a little bit to get to the final answer. Okay, now let's look at problems where the function we're trying to integrate is not exactly a sum or difference of functions and a multiple of a function that we can integrate directly with the power rule, as we can only integrate over a sum or difference of functions. So let's see how we can get out of sometimes a multiplication and or division. So very simply, if I ask you to integrate, say, 2x plus 3 times 5x minus 6 dx. Well, what we have here is a product, so if we keep the function as this is, we can't integrate over a product. But if we multiply out, then we'll have a polynomial and we can use our properties. So multiply out, you get 2x times 5x, 10x squared, negative 12x plus 15x plus 3x, plus 3 times negative 6, negative 18. And you see, by multiplying out the expression, we now have a polynomial, and we can use our properties because we can integrate now over a sum and a difference of functions. So we integrate first 10x squared. The 10 is a scalar multiple, it stays there. Power rule on x squared, x cubed over 3, plus we integrate the second function. 3 is a scalar multiple, it stays there. Power rule on x, x squared over 2, minus we integrate the third function, 18. And if you think of it, well, what function has derivative 18? It's 18, of course, x. And we add plus c. So there you have it. Just by multiplying out the expression, we were able to have a sum, difference of functions, and then we could use our properties to find the antiderivative. Of course, if I gave you something like this, say x minus 1 squared, you can play the same game. X minus 1 squared is x minus 1 times itself. So if you do multiply out, you'll get x squared minus 2x plus 1. And now again, you can use the properties of integration. Integrate x squared, you get x cubed over 3, minus the integral of 2x. 2 is a scalar multiple, it stays there. Integral of x is x squared over 2, plus the integral of 1, of course, which is x, plus c. And you could, of course, simplify by canceling 2 over 2, and your final answer is x cubed over 3 minus x squared plus x plus c. So there you go. Now what if we had, say, a division? So let's look at two examples. So what if we integrated 3x squared minus 6x plus 7, and we'll divide quite simply by x. So if we keep the function the same as it is, we can't integrate over a division, but as we are dividing by a single x, we can divide through each term by x. So let's do so. X squared over x is x, or 3x, minus 6x over x is 1, minus 6, plus, and here I will not write 7x to the negative 1, because this is our exception. This is 7 over x, and we know that 1 over x integrates to ln of absolute value of x. And now we're good to go. We've turned the quotient into a sum difference of three functions, which we can integrate using either the power rule or the special case. So integrate 3x, you get 3x squared over 2, minus integrate 6, you get 6x, plus 7. Now you're left, if you factor the 7 out, a 1 over x, and of course, that's the special case. The integral of 1 over x is the ln of the absolute value of x, and finally plus c. So that's it. Now let's look at one last example. What if we had a division? So I'll take the same integral, but instead of an x, I'll have a x plus 1 on the denominator. Let's see how we can still get around it, but the division will be a little bit more interesting. So again, we are trying to integrate over a division. We cannot do it directly, but because we have an x plus 1, not an x, we can't just divide across each term by x plus 1, because then we won't get the same kind of nice simplification. But we're still trying to divide two polynomials. We can see what would come out if we were to apply, say, long division. So let's divide this quadratic by x plus 1 and see if somehow this new form gives us a simpler function to integrate. So 3x squared minus 6x plus 7 dividing by x plus 1. Of course, this is the French way of writing it out. If you went to an English high school, you just flip the divisor and the function being divided. So what times x is 3x squared? Obviously 3x. Multiply by 3x, we get 3x squared plus 3x. We subtract. 3x squared minus itself is 0. Negative 6x, negative 3x is negative 9x. And 7 minus 0, of course, plus 7. The degree is 1, the degree here is 1. 1 is not less than 1, we have to do one more step. What times x is negative 9x? Negative 9, multiply across, negative 9x, negative 9. Subtract, negative 9x minus itself is 0, cancels. 7 negative negative 9, 7 plus 9, 16. So now we have our quotient and our remainder. So, what does that mean? It means that the function 3x squared minus 6x plus 7 over x plus 1 is equal to the quotient 3x minus 9 plus the remainder 16, but over, of course, the divisor x plus 1. And that's the result of long division. All it gave us was a different way of writing this rational function. The quotient coming out of the long division plus the remainder over the divisor. And now let's see if we can integrate this. Well, the first two terms are quite easy. We can use the power rule on both of these, no problem. This one looks a little different. If you integrate a 1 over x, you get ln of x in absolute value, but now we have a 1 over x plus 1. Let's make a guess, and then we'll be able to verify if our guess is correct. So let's integrate first 3x. Power rule 3x squared over 2 minus the integral of 9x, as the derivative of 9x is 9, plus, and here's where we'll make a guess. The 16 is this constant multiple, so it stays there. And now we're looking for a function whose derivative is 1 over x plus 1. Well, if it were just 1 over x, we'd guess ln of absolute value of x. So here we'll guess ln of absolute value of x plus 1. And of course we add our plus c. And this was a guess, but the key is you can always verify your guesses, because you're supposed to have found an antiderivative of the original function. So if you differentiate ln of x plus 1, you should get 1 over x plus 1. So let's see. If we differentiate the ln of x plus 1, well, we differentiate ln first. The derivative of ln is 1 over the argument. Chain rule times the derivative of x plus 1, which is 1. So we get indeed 1 over x plus 1, which is the function for getting the 16 that we were trying to integrate. So every time you have something that looks very close to something that you know how to integrate, you can always make a guess. And you can check whether or not your guess is correct by taking its derivative and making sure you obtain the original function. Let me show you one last example of such a guess. But if I wanted to integrate, quite simply, let's go with 4 over 5x plus 6. So again, it's not just over x, it's over 5x plus 6 now. Well, we can factor the 4, integrate 1 over 5x plus 6 dx. And we know the integral of 1 over x is ln of x in absolute value, so let's make a guess here. Let's guess that this will be the ln of 5x plus 6 in absolute value. Of course, plus c. So now we're guessing. We're saying this is almost 1 over x. If this was 1 over x, we'd get the ln of x in absolute value. This is 1 over 5x plus 6. So we'll guess that the antiderivative is ln of 5x plus 6. It's just a guess. Well, we can easily verify if this is the right answer by taking its derivative and making sure we get this function. So I'll ignore the 4 because it's already there. So if we differentiate ln of 5x plus 6, do we get 1 over 5x plus 6? So we differentiate the ln of 5x plus 6 in absolute value. Chain rule, we differentiate the outside function ln, which gives us 1 over the argument, 5x plus 6. But there is still a 5x plus 6 left over. By the chain rule, we have to multiply what we have so far by the derivative of what's left over. The derivative of 5x plus 6 is, of course, simply 5. So our function is not 1 over 5x plus 6, but 5 over 5x plus 6. We just rewrite this. So this is the wrong guess. If this was right, the derivative of this function should be 1 over 5x plus 6. But our derivative came out to be 5 over 5x plus 6. But you're thinking, well, we're only off by a constant multiple of 5, so we can fix the problem. What if we squeeze in a 1 over 5 in here? Well, then we take the derivative of 1 over 5 times this. But as 1 over 5 is a constant multiple, it will just remain in front of the derivative. And so in the end, we'll have 1 over 5 times 5, which will cancel, and we'll get our 1 over 5x plus 6, the function we were hoping to obtain. And so you see, even sometimes when you make a guess, and initially your guess is wrong, if you're off by a scalar multiple, you can always divide by it to fix your answer. And so in the end, we're left with 4 over 5 ln of 5x plus 6 in absolute value plus c. And the derivative of this function, if I include the 4, is 4 over 5x plus 6. So don't be afraid to make guesses sometimes, but don't just guess and hope that this is okay. Find the derivative of your answer, see if it is the original function, and if you are ever off by a scalar multiple, divide your guess by it, and this will fix your problem. And that's it.